Okay, so as people are kind of meandering in, let me start the seminar off. And I'm Shafi, the director of the Simons Institute. And as I think most of you know, the Simons Institute is an international venue for collaborative research in theoretical computer science, established in 2012 with a very generous grant from the Simons Foundation. And it's my great pleasure to welcome you to the third talk in a new series, which we call the Breakthrough Lecture Series. We launched it past summer, and it highlights substantial advances in the field of theoretical computer science. And this talk qualifies big time. But before I introduce the speaker, I want to sort of talk about the question and answer etiquette here. So we have people in the audience here at Simons. And if you want to ask a question, just kind of pipe up and I will give you the mic and everybody can hear it. I think people offline, namely not in the auditorium, are all in webinar form. And the way they ask questions is by putting them in the Q&A. And as I notice them, I will kind of alert Irit to the questions. And I think it's time to introduce Irit. So our speaker today is Professor Irit Dinur. Irit was educated in Tel Aviv University. She got both her BS and a PhD in Tel Aviv. And then she came for a postdoc at Berkeley, actually. She was in the Miller Institute and also a postdoc at the Advanced Study Institute in Princeton and the NEC Research Institute in Princeton. And she then went to Hebrew University, where she was a senior lecturer before joining the Weizmann Institute, where she's now. She was also a fellow at Harvard University, I guess the William Bentinck Smith Fellow, and she's also been a visiting professor there and a visiting professor at IAS. She was a plenary speaker in ICM, International Congress of Mathematicians, in 2010. She's received numerous awards and honors, including the Gödel Prize, the ACM POD's Test of Time Award, Levinson Prize in Mathematics, Erdős Prize in Mathematics, and the Anna Nadiv Bruno Research Award. And her research interests are in complexity theory, in probabilistically checkable proofs, error correcting codes, and there are many of their applications. These days, she is interested in connecting these to high-dimensional expansion, an analog of expander graphs on which she actually ran a cluster a few summers ago at Simons when we were still in person. And it was a very interesting cluster with visitors from around the world. But Irit doesn't only do complexity theory. She has really, for example, she and Kobi Nissim have had actually the first paper that launched differential privacy, what became differential privacy later, and many other breakthrough results. Today, she's talking about locally testable codes with constant rate, distance, and locality, which was sort of a coveted result for a long time. So please join me in welcoming Irit, and the floor is yours.
Wow, okay, thank you very much. Such a nice introduction, and okay, I'll start the talk. Thanks for inviting me to give this talk. It's a very, very new result. It's based on joint work with Shai Evra, Ron Livne, Alex Lubotsky, and Shachar Moses. And I want to thank also the graphic designer who made this beautiful graphics. Hopefully, when the talk progresses, the graphic will make a bit more sense. Okay, so let's start by talking about locally testable codes. These are error correcting codes. For us in this talk, it's just going to be linear error correcting code. So it's just a linear vector space over 0, 1. And the parameters that people always talk about are the rate and the distance. The rate is just the dimension of this vector space normalized divided by n. And the distance is the number of non-zero bits in the lowest weight code word that's not 0. And again, we divide by n. So when we say constant rate and distance, we mean that this is a positive number greater than 0. And we're always thinking about an infinite family where n goes to infinity, but the rate is always going to be at least some 0.1 or maybe 0.9. We'll see. So these are very, very standard parameters. I'm not going to talk about them anymore. Local testability is less standard. Maybe it's in some circles, but let me define it nevertheless. So code C is called locally testable with Q queries if there is an algorithm that we call a tester algorithm. And this algorithm has access to an input, a word, but it doesn't read the input. Instead, it's given just query access. So it tosses some coins, then it decides on some Q locations in the word, and it only reads these Q locations. And based on the values there, it decides yes or no, accept or reject. And it satisfies the following two properties. First of all, if the word is in the code, then the algorithm is always going to accept. Even though it's only reading Q bits, it's going to always say yes. If the input is not in the code, then we can't really expect the algorithm to reject with high probability because it's only reading a few bits and maybe the code word was only slightly tampered with. So the only realistic thing we can expect is that the rejection probability is proportional to the distance of the word from the code, and that's what we require here. So this is one variant of local testability. There are several other ones. This one is the strongest, so I'm going to just stick to this definition. Q, the number of bits that the tester reads, is called the locality. Of course, the smaller Q is, kind of the more impressive the result, because the algorithm really is not looking at almost anything. It's only looking at a constant number of bits and still making a decision that is going to be meaningful. So small locality is kind of better. Okay, let me tell you a little bit about the history of locally testable codes. Already to tell you, whereas Shannon already in his seminal paper proved that a random parity check matrix will have good rate and distance, he couldn't have conceived of locally testable codes because random codes don't have this property. And really, the only natural way I can imagine of coming up with this definition is through the kind of the journey through the probabilistically checkable proofs, which is indeed how this came about. So locally testable codes were studied implicitly in early works on probabilistically checkable proofs and program checking in the very early 90s. What are these PCPs tell you that any NP proof can be encoded into a PCP proof, another proof that can be locally checked, like you want to locally check a code word. And when you try to prove such a theorem and you try to construct these PCP encodings, you're naturally encoding your NP proof using some encodings. And you imagine that the prover is giving you this encoding. And there is a verification procedure that needs to check that whatever the prover is giving you is actually a correct encoding. So it's almost built into the definition of PCPs. It's not really, but it feels very similar to, and indeed that's how it worked out. PCPs, when you construct them, you want to use locally testable codes to encode the proof. Of course, you need other properties as well. So this is indeed how things went. And during those years, people really discovered the incredible power of low degree functions and polynomials and used them for various properties. And it was it's really fantastic what a diverse set of properties low degree functions have. And in particular, low degree tests show you that polynomial codes like the Reed-Muller code is locally testable. And in works that deal with these objects, locally testable codes more generally were also defined. Dan Spielman, in his PhD thesis, he worked on expander codes, which we're going to describe soon in more details, and also on PCPs. And in his PhD thesis, he kind of writes about an object that combines the two together. And this is kind of a nice paragraph that I want to read. So here he writes this: a checker, and here he refers to a local tester, like what we just defined in the previous slide. A checker would be able to read only a constant number of bits of a received signal. This is the input word, and then estimate the chance that a decoder will be able to correct the errors. Then the checker can instantly request a retransmission of that block before the decoder has wasted its time trying to decode the message. Unfortunately, all known codes with local checkers have rate approaching 0. So I find this really nice because it captures exactly a kind of a wonderful application of locally testable codes, right? You transmit the encoding, but instead of worrying about decoding, which might take some time, just randomly do some checks. And if you see that there's too many errors, you can already ask for a resend. So that's kind of cool. Of course, since no LTCs were known with constant rate, this doesn't meet the kind of the golden standard of coding theory, and codes with a rate approaching 0 are typically considered not realistic. Okay. So this was in the 90s, and then a few years later, Goldreich and Sudan started a more systematic study of locally testable codes as objects of interest on their own. And they also put on the table the question of what's the highest possible rate of a locally testable code. And this spurred a sequence of works that constructed both locally testable codes and PCPs with length growing shorter and shorter. So you always compare the length of the message and the length of the encoding. So in PCPs, you compare the length of the NP witness to the length of the PCP witness. And all of these works that I kind of quickly wrote here construct both objects with length shrinking and shrinking and shrinking. And the state of the art is to have constant distance and constant locality, but the rate is 1 over polylog. So that's going to 0 as the block length increases, but it's still not so bad. And at that point, people were already talking about, whether or not it's possible to get locally testable codes that are so-called good. Good being constant rate and distance, which is like the standard of coding theory. And later we changed the name to, instead of saying good, which is kind of a vague description, we changed it to C3 for constant rate, constant distance, and constant locality. And there was a lot of doubt about, can you even construct such objects? Maybe you can, maybe you can't. Unclear, and people started working also on lower bounds, trying to prove that codes with certain properties cannot exist or must have high rate. I myself was involved in one of these works, but all of the lower bounds were restricted. Another line of work said, okay, let's go from the other direction. Let's insist on the rate being a constant and see what's the smallest possible locality we can get. And these works are also nice because they kind of abandoned the whole PCP paradigm and said, we're just going to focus on codes. And using expanders, they actually got constant rates, constant distance, and locality that is slightly larger than polylog n. It's quasi-polylog n locality. Want to also mention another thread involved in property testing of all these algebraic codes, which was interested in understanding what makes all these algebraic codes and other algebraic properties locally testable. And the role of symmetries, here it's affine invariance, was highlighted and proven that any property that has all these symmetries is going to be locally testable. The most recent research direction in this area is the research direction of high-dimensional expansion. Here, high-dimensional expanders are these wonderful objects that are based on some very broad variety of mathematics. And I first learned about them from Tali Kaufman. They exhibit really interesting local to global features. And I'm going to talk about this more later, but just to say that it was clear that these objects might be very useful for property testing and maybe even for constructing locally testable codes. And as Shafi mentioned earlier, we even had a summer cluster on this topic called the high-dimensional expanders and codes. And I put this slide on because I really like the graphic that Barry made for us. Here you see that they put like the geometric structure, the graph with the triangle, so it's like a high-dimensional object. And on top of it, you have the bits of the code. So it was already clear that we're trying to build codes on top of some high-dimensional object. And the current work that I'm now talking about is going to be along these lines. Okay, so the main result is this. There exist constants r, the rate, delta, the distance, and q, the locality, and an explicit construction of an infinite family of error-correcting codes with the rate r, distance delta, and locally testable with q queries. Okay, so now I want to start the more technical part of the talk. It's hopefully going to be supposed to be self-contained, so please do interrupt with questions. If I can't hear you, then someone can help me here. Okay, so my plan is this. I'm first going to talk about expander codes, which many of us know very well, but I'm going to describe them in some detail just to make it easier to describe the new codes, which really are a second layer on top of the expander code. So it'll be very useful for us. Then I'm going to define a new object that we call the left-right Cayley complex. And this is really like a graph that has an extra layer of squares. This is the second dimension thing. After defining this object, this graph with squares, we're going to define the code on the square complex. And then we're going to analyze some of the properties. Okay, so let's begin. So I want to talk about expander code. So I guess historically, it makes sense to first mention the low density parity check codes of Gallagher. But in interest of time, let me just already talk about Tanner codes, which are a generalization of the LDPC codes. In Tanner codes, you are presented with a bipartite graph called the factor graph, and we see it over here. And the bits of the code, or the code word, is going to be placed on the vertices of the graph over here. So you put 0, 1, 1, 0, and so on. And the constraints are the vertices on the right. Each vertex looks at all of its neighbors. It sees a little local view of the entire code word, and it requires that this local view belongs to some base code. So there is some, okay. There is some base code C0 here, and pardon me until I get the, okay, looks okay. There is some base code C0, and you require that the bit, you require that the bits that this guy is seeing are in the base code. I don't know why it suddenly happened. Okay. All right. Okay. Okay. Maybe you can see here in the bottom right corner, I wrote down the Tanner code. It's all the words labeling the left-hand vertices, such that for every vertex on the right, the kind of local picture that it sees is in the base code. That's a Tanner code. And to tell me, to specify a specific Tanner code, what you need to tell me are two things. One, what is the structure of your factor graph? What's the bipartite graph? And two, what is the base code? And once you give me these two things, I know what the Tanner code is. So Tensor and Spielman constructed such Tanner codes in a very beautiful way using explicit expander graphs. And what they did was they took an expander graph and they used it to construct this factor graph. And this is what I'm going to show now in the next slide. So here are the Tensor and Spielman codes. You start out with a deregular lambda expander graph G. Now, I'm not going to formally define lambda expander, but let me just say, for those of us who know, you look at the adjacency matrix of the graph and you look at the eigenvalues. And if all the eigenvalues except the top one are below lambda, I'm thinking of now about normalized eigenvalues, then you call the graph a lambda expander. And we know of explicit families of such expanders. So you can construct them in polynomial time deterministically and so on. You take such a graph. If you're not so familiar with these graphs, let me just say that these are graphs that on one hand, every vertex only sees D neighbors, so they're very sparse. But on the other hand, they're very well connected. No matter how you split the vertices into two parts, there's going to be many, many edges crossing between the parts. Okay, so you take this graph and you put the bits of the code on the edges of the graph. Okay, so here are the bits of the code. And you take a base code, and the length of the base code is going to be D, the regularity of the graph. The constraints are going to say for every vertex, I want to look at all the edges touching a vertex and have them belong, have the bits that I see there belong to the base code. So you can see down here the factor graph. Let's see if this is going to work for me. The factor graph over here, you can see that for every edge, I put a vertex on the left. And for every vertex here, I put a vertex on the right. And this vertex just looks at all of the edges touching it and sees that these bits belong to the base code. Okay, so this is quite standard. And let me quickly run through the analysis because it's so beautiful that you can really do the analysis of these graphs very, very elegantly.
Irit, sorry to disturb, just to make sure, because you're starting to dive in terms of terminology. So the code here is a set of functions, yeah? So it's which map edges to bits, yeah?
Right. Okay. When mapping edges to bits, just think that every edge is labeled by a 0 or a 1.
Okay.
Every edge is labeled by a 0 or a 1, and the constraint is that if you look around a vertex, then you see here, 1, 1, 1, 1. This string of length 4 needs to be in the base code. Okay, let me try to see how many code words are in this code. What's the dimension of this space of code words by just simple linear algebra? So how many functions do I have on the edges? Well, the dimension is the number of edges. 2 to the number of edges is the number of functions. So the dimension, the ambient dimension, is just the number of edges. Now, my code has some linear constraints. So I'm going to count how many linear constraints I have, and this will restrict how many functions I end up having in my code. So how many constraints do I have? For every vertex in V, I have a bunch of constraints. These are the constraints that say the edges around this vertex need to be in C0. How many constraints are there? This is exactly the number. This is the number of constraints to define the code, the small code C0. So I have this many linear constraints per every vertex. So the total dimension is the number of edges minus this number of constraints. And you just do the calculation and you see that it's the number of edges times 2R0 minus 1. So this becomes positive as long as R0 is above a half. So as long as your base code has rate above a half, this definition makes sense and the code is going to have a linear dimension. Okay, now what about the distance? Okay, let me erase some of the clutter here. To prove distance, you really rely on the expansion. So if you understand just a little bit spectral expansion, proving distance is really a piece of cake. Let's not go through the proof, but let's just think about it intuitively. If I want to prove distance, I need to think of some code word that's not all zeros. Okay, so it's some code word. It has some non-zero edge, right? So for example, this edge has a 1 on it. So now I look at one of the vertices, one of the endpoints of the edge, and I see that it hardly has a single 1 on it. So it means that the word around this vertex is a non-zero word. So there must be delta naught times the other ones. So this must be a 1, this must be a 1. Okay, so now I can move to these 3 vertices. Okay, each one of them touches a non-zero edge. So again, it must have a few non-zero edges. And this propagates and propagates and propagates. And using the expander mixing lemma or the Alon-Chang lemma, you see that the code has distance. Okay.
So, Irit, there's some questions in the chat. If you can just quickly, a specific question on this slide, I think.
Okay, can I see it?
On the Q&A, I think you can see.
Should there be n edges as well? Since we're on n, here is the number of edges.
Yeah.
N just denotes the number of edges in the graph. Yeah, that's a good question. So usually n denotes the number of vertices, but here n is going to be the number of edges, the number of edges here. This is n, and this is going to be, so n will be the number of edges, And the number of vertices is, I don't know what letter to use for it.
And there's another question here is, should there be an order on the edges?
That's a good question. Yeah, okay, let me answer that. Every vertex, when I say that a vertex looks at its edges and sees a bunch of bits, here it's going to see 1, 0, 1. How does it know what it needs to have an order on the edges to know how to associate this with a string of 3 bits, right? So we can assume here, I'm just doing it implicitly, that the vertex has some arbitrary order on each vertex has an order on its edges. Okay, any more questions?
No, I think
How small can I make Q? Okay, I don't know, and let's talk about this at the end. Okay, one of the wonderful aspects of these expander codes is that not only do they have constant rate and distance, they actually allow for a formal proof of linear time decoding. I'm not going to go into it here, but this is a really, really cool algorithm. For me, what we care about today, I'm going to talk about the local testability of these codes. Are they locally testable? So the answer is no. Typically, they're not going to be locally testable, and I want to spend this slide to explain why they're not locally testable. Okay. So firstly, let's observe that when I defined the Tanner code, I said that you give me a factor graph, and then every check node checks that you belong to some C naught. But really, there's no reason to put the same C naught at every location. We can define the expander codes so that this vertex will ask whether these bits belong to one base code, and this vertex can ask whether these bits belong to another base code. Nothing in the analysis will change. We just counted linear constraints, and we use the fact that the base codes have distance at least some delta naught. So that's going to still be legal. Okay, so now we can do kind of a thought experiment. Think of the expander codes as we define them, and then choose one vertex, say this guy, call it V0. And on V0, you're going to just remove one of the constraints. Okay, so you remove one of the constraints, and the code, the C0 on this vertex only, is slightly larger. It has double the number of words. Okay. Now, what happens to the global code? Typically, all of the constraints are linearly independent from each other. So when you remove one constraint, the entire global code doubled in size. The dimension increased by 1. So what does this mean? It means that now new code words have appeared. New code words have appeared, but still all of the analysis goes through, in particular the distance. So all of the new code words together satisfy that they are all very far from each other. In particular, look at one new code word. It's far from all of the old code words. Okay? What does it mean far? It means that it's far by a linear number of bits from all of the old code words. But on the other hand, it satisfies all of the constraints of the new code, which means that it satisfies, it satisfies this constraint and this constraint. It satisfies all of the constraints except for this constraint. The only one that it doesn't satisfy is the constraint on V0. Okay, so this is a problem, right? It's a code word that's far, but it violates only one constraint. It's a nightmare for proving local testability. It's like the worst counterexample. It's very, very far and satisfies almost everything. Okay, where was the problem? The problem was we were able to change one constraint and increase the code. There was no connection between different constraints. And in the codes that we will construct, even if you remove some constraint locally, it won't affect the code because the constraints will themselves be dependent on each other. So we will see this soon. Any questions before I move to the... Okay, so far we basically talked about kind of well-known things. Now I want to move to the one level up. So now I want to talk about pushing expander codes to the next dimension. basically, if we previously had a factor graph with vertices and edges, now we're going to add squares. That's like faces of one more dimension up. And if previously we had the bits here and the constraints here, now we're going to move the bits to the squares and move the constraints to the edges. See, the bits are here and the constraints are here. And the vertices, they're going to supply us with dependencies among the constraints. We'll see that. Okay, so how do we do that? We have in our mind a graph that not only has vertices and edges, it also has these 4 cycles that we call squares. And there's going to be some factor graph like we have here on the right. Okay, so let's define such an object. Before I define it, I want to define a Cayley graph. It's a very, very standard object, but just to be sure, to define a Cayley graph, you start with a finite group G and a set A of elements. We assume that it's closed under taking inverses. So if A is in the set, A inverse is in the set. And from these, you build a graph. You put vertices for every element in the group, you put a vertex. And you connect a vertex G to a vertex A times G. These are the edges. And notice that it's an undirected graph because if you're at vertex A times G and you multiply by A inverse, you move to A inverse times A times G, which is back to G. So it's an undirected graph. This is very standard Cayley graph. Okay, now what are we doing that's slightly different? We're going to take 2 Cayley graphs, one with the set of elements B, A, and one with the set of elements B. Okay, A for that. Okay, so we're going to have 2 Cayley graphs. Cayley graph of G and A is the graph with this set of edges from G to AG, and the Cayley graph of G with B is another graph with this set of edges from G to G times B. Okay, there's a slight difference between the A graph and the B graph, and the difference is that for the A graph we multiply on the left A times G, and for the B graph we multiply on the right G times B. And what difference does this make? Usually it makes no difference, but here it gives you this commutativity because you can start from a vertex G. You can first take a red edge and then a blue edge. So first take a B edge and then an A edge, or you can first take an A edge and then a B edge, and you'll end up in the same location. So this gives you a lot of squares. Okay, and this is something we will build on. Here is the square. So I highlighted it, I filled it to emphasize the fact that we don't only think of it as a cycle, we think of the square itself as an object. Okay, so let's look at it a bit more closely. Focus on one vertex G and 2 generators, A and B. So A takes me from G to AG, and B takes me from G to GB. Okay, and these 3 things, A, B, and G, this triple defines for me a rooted square, right? Because it defines for me this square, but it also specifies the root G, right? I mean, the same square can also be defined by a different triple, right? I can start from AG here, and then I can take the generator A inverse to move to A inverse AG, which is G, and I can use the generator B to move here, AGB. So this would correspond to using A inverse, AG, and B. So this would correspond to this triple, which is the rooted square, which is the same square as we have in the picture, but with the root AG. Okay, so every square has 4 different roots, right? And okay, maybe I can question. Clever, yeah.
There's a question in the chat. The squares could be degenerate. Is that a problem if GA equals to GBG?
Right, thank you. So I don't think it's a problem, but let's, for the talk, assume that this never happened. So that's a very good point. So you could potentially have that AG equals GB. In other words, G inverse AG equals B. And let's just assume a non-conjugacy condition. None of the A's are conjugate to none of the B's, so this never happens. All the squares are non-degenerate. Good catch here. Okay, so there's 4 different roots, and we're going to define a non-unrooted square, or just a square. We write it with these square brackets over here, and it's just this equivalence class of the 4 rooted squares. Okay, so basically you have all these rooted squares, and you bunch them into small equivalence classes, and these are your squares. And the square naturally contains the edges in the picture, right? So the edge G to AG, the edge G to GB, and so on, and these 4 vertices. And formally, the set of squares is exactly the set of all triples A times G times B divided by this equivalence class relation. Okay, questions? Someone is asking, aren't Cayley graphs usually defined on abelian groups? G here is non-abelian. G can be abelian, but for us, we want the graph to be an expander, and you won't get any constant degree expanders if G is abelian. So no, Cayley graphs certainly are defined for all groups, also non-abelian groups. I think this object is also interesting for abelian groups, but I mean, it's known that abelian groups require a logarithmic number of generators to become expanders. Okay. So let's now summarize just the definition of this complex. So we started with a finite group, and we took 2 sets of generators closed under inverses. I mean, formally, they don't need to be generators. The graph will just not be connected, but it's not so important. Okay, and now we define the complex by the following 3 things. The vertices are just the group elements. The edges are the Cayley graph edges, the union of the 2 Cayley graphs. And the squares are, like we said, the equivalence classes. And we're going to say that this Cayley square complex is a lambda expander if each one of the Cayley graphs, the A1 and the B1, are each lambda expanders. And almost standard things that people have already studied a lot imply that for every lambda, you can get explicit infinite families of bounded degree left-right Cayley complexes that are lambda expanders. The only non-trivial thing is if you go back to that question about having the squares non-degenerate, you need this non-conjugacy condition. So you need to work a little bit hard to come up with sets of generators A and B that satisfy this non-conjugacy condition. Okay, but it's not so hard to construct. Okay, so let me talk a little bit about some properties of these complexes. Okay, so let's focus on one edge connecting G to AG. Who are the squares that touch this edge? So for any B neighbor of G, say GB1, there's also the same B neighbor for AGB1, and this will be closing a square, okay? You can see kind of by picture that the set of squares touching AG are like pages in a book. The spine is the edge GAG, and each page is really labeled by one element from B. So these pages are kind of naturally identified with B. Symmetrically, if you look at an edge from G to GB, who are the squares touching this edge? It's all these squares are naturally identified with A, right? This set from G to GB is like a spine, and all the squares are like the pages in this book. Okay? So every edge has like a book of squares around it. Okay, now let's look at the vertex and what kind of squares touch a vertex. Okay, so this picture looks a bit scary, but let's go through it slowly. So a vertex G, this guy, has neighbors for every element of A and for every element of B, right? So let me write it. So I have here A1, A2, maybe I call it A1G, A2G, A3G. This is the name of these vertices. And there's also the neighbors on the B side. This is GB1, GB2, GB3. Okay, so this is the name of these 6 vertices. Now, what are the smaller dots in here? These are not neighbors of G, but they're like the tips of the square. So if I choose, say, A3G and GB3, then this makes a square. You take this edge, maybe I try it, from G to A3G, and from G to GB3, and then I can close the square like this. This is one square touching G. There are other squares that touch this edge from G to A3G, right? This edge, you can also take another B neighbor. For example, you can take from G to GB2, and from A3G to A3GB2. Now I sound now like a programmer. Anyway, you get this square, and you can also move to the third B neighbor, like this. And you see here that you got 3 pages in the book whose spine is this edge. Okay? And more generally, you can see that the neighbors, that the squares that touch G can be arranged, I hope you see it, in this A by B matrix, okay? Where the square corresponding to, I don't know, this location is the square that is called A1, G, B2. Because I took this row and this column. Okay, this is already getting very messy. Okay, so all the squares touching G can be arranged in an A by B matrix. And what else should I say about this? Okay, and the squares that touch an entire edge correspond to either a column or a row in this matrix. This column corresponds to this edge, and this row corresponds to this edge. Okay. Any questions so far? Is it possible that 4 vertices in one of the original graphs, say A? Yes. Good question. So the question was, maybe this graph has many other 4 cycles. We don't care. We only care about the ones that that alternate in colors and are of the kind we defined. What kind of groups give these explicit examples? Okay. So these are like the matrix, 2 by 2 matrix groups, like the kind that give the LPS expanders, more accurately, the higher dimensional ones, like the LSV expanders. So these are, think of particular 2 by 2 matrices over some large field. These are the groups that you can use for these graphs. Any more questions? Do we need an assumption to guarantee that GB1 is not equal, or does it not matter? Right, so we talked about that, and no, okay, you asked GB1 not equal to A GB2. All these non-conjugacy things will take care of that. Okay. Okay. So finally, I just want to remark that maybe now this explains the graphic better. You have all these squares and they're kind of one touching the other, and it's kind of a very complicated mess. But when you look just at local pieces of this mess, then you can put some order into it. I also want to comment that this specific construction is an example of a square complex. Square complexes are very well studied, and you also have cubical complexes, meaning higher dimensions than just squares. You can easily construct them just by taking Cartesian product of graphs. You will get such, if you take 2 graphs, you're going to get a square complex. If you take more, you're going to get a d-dimensional cubical complex. But we also know of better constructions than just products, constructions that are Ramanujan for the correct definition of that. Somehow, all the constructions that we know, and this is well studied, didn't give us what we need, whereas this construction does give it to us. It's curious that Cayley graphs have been studied for maybe over 100 years, but I don't know if these objects were looked at before and were useful. So I find that curious. Okay. So now I finished talking about the square, the left-right Cayley complex, and I want to talk about the code. So maybe let's check if there are any more questions. Okay, we answered all the questions.
It looks like it.
Okay. Okay, so let's define the code. So just like in the expander codes, we had two components, an expander graph and a base code. Here, we're going to have two components, the square complex, the Cayley, left-right Cayley complex, and the base code. So we're going to have two base codes, one for the A generators and one for the B generators, so CA and CB. And you can assume that A equals B in size, so that you can take just one code C0 and have CA and CB just be copies of C0. And then you define the code. You're going to put the bits on the squares. So what I mean by that is that your code words are going to be functions that label every square with a bit. So it's functions from the squares to bits. Just like before, we had functions from the edges to bits. So that's the code words, and they have to have some kind of constraints. So the constraints are going to be given by edges. Every edge is going to look around at all the squares around it, so like all the pages in the book of this edge, and it's going to require that these bits line up to be an element in the base code. And remember, there was a question that said, do you need to order the edges in the expander graph? Because how are you going to know if it's in the base code? Maybe the bits are like this, or maybe they're like that. So here we have a natural ordering using the Cayley generators. So formally, this is the definition of the code. So let's read it slowly. The code contains all functions on the squares to 0, 1, such that for every edge of the form G, GB, when you let A run freely, so for all values of A, what you see here is a function from the set A to 0, 1. This function needs to be in CA. So geometrically, it means that you have an edge. You look at all the book around this edge, it lines up, you order it according to A, and then this needs to be in CA. And symmetrically, when you fix an edge of the form G, AG, and you let B run freely, this is a function on the set B, and this needs to be in CB. Okay, so this is the definition of the code. Now that we have the code defined, we can start asking what is the rate, what is the distance, local testability, and so on. So let's talk about the rate. The rate analysis is exactly like we had in the case of the expander codes. Well, not exactly, but conceptually, it's exactly the same. To prove that the rate is positive, you just need to see how many degrees of freedom you have. So the original degrees of freedom is the number of squares. How many do I have? How many triples do I have? I have G times A times B. That's the number of rooted squares. And I need to divide by 4. That's the number of squares. And then I need to subtract the number of constraints. Maybe some constraints are not independent. That's only going to be in my favor. So this is only a lower bound. So I have A constraints and I have B constraints. For every A edge, so how many A edges do I have? I have GA divided by 2. For every A edge, I'm going to have the constraint that this set of squares needs to be in the B code. So how many constraints define the B code? It's B times 1 minus R0. Pretend that I choose the same C0 for both A and B. Okay. And also allow me not to write cardinalities in every place because it will be hard to read. Okay, and symmetrically, I also have all the B constraints. So for every B edge, this is the number of B edges, I have a constraint that you belong to the code CA. So the number of such constraints are A times 1 minus R naught. And if I just open this up and I do the calculation, I get that you get G times A times B divided by 4, that's the number of squares, times 4 R naught minus 3. So that's exactly what I have here, because I need to divide by the number of squares. So I need to remove this when I normalize. And I get that the rate is positive whenever R naught is above 3/4. Previously, we needed R naught to be above a half. Now we just need it to be above 3/4. What about the distance? So I'm not going to do it now, but the distance follows a propagation argument, just like before. Suppose you have some non-zero code word. So there's some square that's non-zero. Look at that, a vertex touching this square, or look at an edge touching this square. This edge must have many other non-zeros because CA, the code there, has positive distance. So this means that other squares are non-zero, and you keep propagating and you see that there is some positive distance. Of course, I do need expansion for this propagation to work, so I do need that delta naught is bigger than lambda. This was the same issue that we had in expander codes. And maybe I forgot to say then, I'll say it now. Nice way to think about expander codes and Tanner codes is that if your base code has some property like distance, then the expansion allows you to globalize this property and have the entire code have this same property, distance. Okay. So these were nice things, and we already had them in the case of the one-dimensional expander codes. Let's look at something that's new here, the local views from the point of view of the vertices. So the claim here is that the local views are tensor codes. So what are the local views? Remember this picture where we had a vertex and we looked at all the squares touching the vertex and they were lined up in this A by B matrix? So the claim is that if I look at these squares and I put them in this A by B matrix, the local view that I'm going to see is going to be of a tensor code. So formally, I'm starting with a word in the code. Okay, so it's a labeling of all the squares with bits. And now I fix some vertex G, and I look at this part of the word. So I fix G, and I let A run freely and B run freely. And that's how I place these bits in this matrix. Okay, this is just defining a matrix for me. And the claim is that this local view must belong to the code CA tensor CB. If you're not familiar with this notation, it just means that all the columns are in CA and all the rows are in CB. This is the definition of this tensor code. And this is really just from the definition. I copied here the definition and notice that I fix B, meaning that I fix some column, and I let A run freely. And the definition says it must be in CA. And this part says that if I fix A, so I'm fixing a row, and I let B run freely, I must be in CB. So it's basic that the local view is a tensor code. That's interesting because tensor codes have non-trivial dependencies between their constraints. You know, for example, oh, I won't say any more than that. But so here is the theorem. The theorem says, if you start with a left-right Cayley complex, that is a lambda expander. That's one condition that you need. And if your base code CA and CB are locally testable, so here I wrote row robustly testable. I'll say what that is in a minute. So if these two conditions hold and there is a correct relationship, so the expansion is sufficiently small with respect to both the local distance and the local testability, if these two things hold, then the resulting code is locally testable. Okay. So it's very similar to the case of expander codes. There you said, if the local code has good distance, and there is some relationship, lambda is less than delta naught, the distance globalizes. And here you're adding this extra thing. If the local code also has local testability and there is some relation, then this also globalizes. Okay, so this is really like in line with this philosophy of high-dimensional expansion, where the expansion can be used to lift things globally. So when you say something is locally testable, let's say what the test is going to be. So the test is this: select a random vertex uniformly, and then you read your given code word, this function on the squares, on all the squares that touch this vertex. So basically, you just read this entire little matrix. Maybe I forgot to emphasize, but let me just say it again. When we think of a Cayley complex, we think of A and B as constant, and the size of the group goes to infinity. Okay, so this is like a constant number of bits, and the graph is going to, the size of the graph is huge. So you read this entire little matrix, and of course, how do you accept or reject? You accept if it belongs to the tensor code. So that's the test. And what is the main thing that we need to prove? It's this inequality. It says that the probability, the fraction of vertices G on which the local view fails to be a tensor code word, this fraction is an upper bound to the distance of F from the code. Okay, so you can't have a situation where F is only failing on a few local views, but somehow it's very far from the code. This is something that happened earlier, but in this situation, you can't have it. And notice also that unlike in the Tanner codes, okay, sorry, this code is a Tanner code. We saw the factor graph. So this code is a Tanner code, but it's not an expander code like the experiment codes were. And indeed, there you could have C0 be different at every location. Here, I can't have that because even if I change the constraints around one edge, still the fact that I require this entire thing to be a tensor code, it implies that this will satisfy also the constraints that I removed. Okay, let's see. So any more questions? Okay, say I went pretty slowly. When did we start? How long do I have?
Can you hear me? Why don't you take 4 minutes, so 2 minutes over?
Okay. All right. So let me skip this. This is explaining what exactly is the condition on the base code that you need to satisfy the theorem. Not every base code works, but random LDPC codes are going to work, and I'm going to skip that. I wanted to show some proof of local testability, but I feel like, okay, I'm just going to kind of go over the algorithm. So how do you prove that something is locally testable? You start with a word that has some probability of rejection. And in your proof, or at least in this proof, you show an algorithm to reconstruct a nearby code word. And this algorithm is really like a simple self-correction algorithm. So let's look at the algorithm. You start with a word. First step, for every vertex, you look at the entire local neighborhood of the vertex, and you find an actual tensor code word that's closest to the view that you see. The view that you see doesn't have to be a valid code word, so you correct it in some way. But then the different local views might disagree with each other, and so you define a progress measure, which is the number of edges that are in dispute. So G thinks something, and G prime, the neighbor, thinks something else. This edge is in dispute. And then you do this local correction where every vertex looks at its neighbors and sees and thinks, maybe I can change my entire tensor code word to be in better agreement with my neighbors. If you can do that, go ahead and keep doing it until you're stuck. At this point, if there's no more disagreement, zero disagreement, that's it, we're happy. We can output a code word. And that's actually what we prove is that if the probability of rejection was small, you will never be stuck. We prove it in the other way. We say that if you're stuck, must be that the rejection is very high. Okay, now I'm a bit out of time, so I apologize, but I skipped this. Trying to explain here why the local testability is required for the propagation to work. Somehow, to prove that the rejection must be high, you show that if there was even one dispute edge, there must be more dispute edge and more and more and more, like in the case of distance. And so there's a lot, if you got stuck, it means there's a ton of rejection. But for this won't work unless the local code has some local testability. Okay, I'm not going to do it, but okay, so let me just kind of finish. So the main result is that there exists R delta and Q such that an infinite family of local testable codes. And how do we do it from the components that we discussed? So we start with a family of base codes like random LDPC codes that have high enough rate, and constant robustness is this local testability property, and constant delta distance. Then you choose lambda to be small enough with respect to these parameters. And then you choose a family of left-right Cayley complexes for this small lambda. This dictates the size, the size of AN and BN. It's some constant D that depends on lambda, which depends on delta and rho. And then you output the code, which is based on the Cayley complexes, together with the base code, which you choose on length D. Okay, so you can do it. Okay, so to finish, let me just say some high-level thoughts about high-dimensional expansion. The idea of using high-dimensional objects, here we have these squares, to construct LTCs instead of just one-dimensional expanders. This idea has been around for a few years. As we said, it started from these high-dimensional expanders, which have these marvelous local-to-global features. I first learned about it from Tali Kaufman, and it was obvious that this is very interesting. It also involves a lot of areas of math that I didn't know a lot about. And initially, we thought that this would involve very complicated things, but somehow things simplified. I think it could have been much worse than it is. There have been a lot of works showing this local to global, and although this work doesn't use these specific objects, it does use the same ideology, I guess. Specifically, we had this work that started in a summer cluster at Berkeley with Harsha, Ronsvi, and Dickstein, where we proved that if you define a code on a high-dimensional expander and locally it's an LTC and there's some other extra agreement test, it's a technical condition, then you can globalize and prove that the entire thing is an LTC. And this paper, I think, is really what gave us confidence in this work to kind of push and try to get this LTC. It didn't have very good faith in terms of, it got rejected from plenty of conferences, but I guess it was hard to believe that this program will materialize somehow. But for us, I think we did believe it. And recently also I saw a similar schema in a recent paper by Kaufman and Oppenheim. So the main problem that we were facing was how to instantiate this idea of defining a local code and globalizing. When you actually try to do it, it's very difficult. We had some conjectures, we couldn't manage to do it. And luckily, this whole square complexes with these tensors was a way to circumvent these difficulties. I think this is still a super interesting question. So here are some questions. Can you materialize that hope of constructing codes on the Brought-Tietz quotient building, whatever? That's one question. Another question is about these left-right complexes that are new objects and kind of interesting. Is there a three-dimensional version for these or more dimensional? It seems that this is very strongly relying on this left-right multiplication, but I don't know. And of course, the last question is, you know, LTCs came from PCPs. For a long time, people believe that they're related and you can always do them together. Can you use these things to construct PCPs? I don't know. Okay, I'll end here.
So first of all, thank you very much. And for your beautiful result and talk. And even though we're out of time, are there any questions in the audience here?
I have a question.
Go for it.
A beautiful result. So it sounds like you're not actually using high dimensional expansion anywhere. It's just basic graph expansion, right?
It's based on just basic graph expansion, but there is something that's high dimensional in that when you analyze the local testability, the part that I skipped, you analyze a walk that goes from edge to parallel edge. And it goes from an edge to a square to the parallel edge in the square. So to me, that's like a higher dimensional walk because you're not going through the vertices. But yeah, I don't know.
Thank you.
Any other questions? I guess there was a question, which is your paper publicly available? And I think earlier people asked if you would give us your slides. We definitely will post your recorded talk.
Yeah, I definitely will give the slides, and the paper is like almost, it's not publicly available yet. I hope to get it by the talk, and I apologize, but maybe in a couple of weeks. I'm giving another talk in a couple of weeks at IIS. It'll be more detailed, and by then I really hope the paper will be out.
Okay, absolutely great. And thanks again. And thank you, Irit, and everybody for joining.
Thank you.
Bye-bye.